synthesis gas conversion by David Sachtler.
It's a pleasure for me to be here as well. It's fallen upon me to review some of C.O. Bennett's work over the last 10 years or so on the Fischer-Tropsch type reactions on iron and nickel catalysts. He's done quite a bit of work with titrations with hydrogen itself, and especially with iron, you see a nice spectrum almost of reactivity and several different types of intermediates or side accumulations, carbonaceous deposits, and also some experiments with deuterium, which help to give us an understanding for what the chemical nature of these intermediates and other species are. So I'm going to talk about three catalysts: the iron, 10% iron on alumina, 10% iron on titania, and 10% nickel on alumina. Both the aluminas are Alon C from Digosa, and the titania is the P25 from Digosa. These are some of the physical properties of the iron on alumina catalysts that we studied and accumulated over the years. There's a BET area of about 100 meters squared per gram. We think there's something like 100 micromoles per gram of surface iron that is exposed. The chemisorptions are, of course, difficult to do because of the activated nature of the absorptions. But by TEM and X-ray and so on, we think that the iron on aluminum is around 200 angstrom chrysolite size. And if you try to reduce that iron catalyst with hydrogen at 460 degrees C almost overnight, you'll get to about 76% reduction. So there's quite a bit of oxide left over. Reactions and tests were done over a series of years, but the most recent work was done with this experimental microreactor. I'll show you this because it has some special features that are useful in the isotope experiments. And it pretty much comprises or contains all of the information and knowledge that Bennett's group has accumulated over the years. The narrow gas inlet and exit tube, so that at our flow rates that the gas is coming through pretty much flow with plug flow. And there's not a lot of dispersive mixing there. But then when you come to the mixed volume of the reactor, this is a shallow and wide bed, so that the plug flow velocity of the gas coming through slows way down, and this helps to increase the diffusive backmixing of the gas. And we think that this volume is actually gradientless under reaction conditions. Just drive home that point a little bit more. These are some mixing curves, and they're given in a normalized and dimensionless form, so that we start at the initial condition of 0 and final condition of 1.0. Z is a dimensionless variable. The curve F is what I call the forcing function of just the instrumentation. If you switch from one gas to another, you'll have a switch, say, that's following the argon signal in a mass spectrometer. You'll find that the system rapidly flushes out and convert and remove all the argon in the feed line and so on very quickly over the course of 2 seconds or so. With a gas chromatographic valve, you can switch the reactor in and out of the system, and if we have the reactor switched into the system, then we get the curve M, which is the so-called mixing curve. That contains any backmixing that occurs in the reactor, plus any backmixing that occurs in the feed line and so on. So there's two things there together, but we've been able to simulate both the forcing function and the mixing curve fairly well with a series of CSTRs, and it seems to agree, surprisingly enough, with the fact that, or the interpretation that the mixed volume in the reactor is gradient-less. So that's very convenient for some of the mathematical stuff. At any rate, back to iron. This is what happens if you start up the reaction over 10% iron aluminum catalyst at 270 degrees C, and you use 10% Cl with balance of hydrogen. Initially, the catalyst is clean, covered with hydrogen, and the surface is quite active. So there's actually a spike in methane production that's not really easy to see there in the figure, but there's quite a large spike, and this rapidly is subdued. And Bennett's interpretation of that is that you have clean sites which very quickly become covered over with an active species we think is CH, and that this is sort of a self-poisoning type of reaction because the hydrogen that you need to convert the CH is also on the same sort of site, so the more CH you have, the lower the reaction rate gets. So you have this very high rate initially that comes down. And then there's more curious behavior. We have a minimum, and Bennett would love to point out that most people, if you were to use gas chromatography, you'd miss that initial spike. But at any rate, after the initial spike, there's an increase in the reaction rate, and the interpretation of that is that there's consumption of the dissociated CO, the carbon in that CO, going to form the bulk carbides, and also this inactive surface carbon, which we think is probably something like the filamentous carbon that's been observed sometimes. After that period of carbon accumulation is over, then you go into a more or less steady state or slowly declining rate of reaction, and that's if there's a decline there, it's because of we think the accumulation of surface carbon. So there's really three rate regimes here. One is in the clean catalyst where the rate's very high. You have CH, and then there's the slow accumulation of bulk carbide and inactive surface carbon, and then finally the slow deactivation of the catalyst owing to graphitic carbon accumulation.
Excuse me, is that very fast initial rate catalytic or stoichiometric? I mean, how many turnovers?
Let's see. I think that to explain it best, I can't tell you how many moles per surface site are produced, but I would think that it was probably less than 1 methane per surface site.
So it might not be a true catalytic reaction.
I don't think so, no, because well, it's certainly not a steady state. You have some very active sites, and it's almost as if you had a CO hydrogenation on the catalyst that did not dissociate CO. It's the same concept where CO poisons its own hydrogenation. It's a negative order reaction in its own population. And so there's a competing series of steps there, and you cross through a maximum because initially, of course, the rate has to be 0 because of the 0 coverage of CH. The high coverage of hydrogen makes it, helps it rise, so it comes up and down. With regard to the bulk, most of our work was done, and these are the results of that work. There's a couple of different forms of carbide that are formed anyway, given on an oxide-free basis here, I think. Same temperature as before. Hydrogen goes to CO hydrogen, at which point the carbides slowly build up over the course of a couple hours. And then if you switch to hydrogen, you can reduce the carbides. But that occurs very slowly also. But it's been known since at least 1948 bulk carbide is not terribly important in the Fischer-Tropsch synthesis over iron. That's due to Hammett's work. There's a figure that I think of as classical for Bennett. This has to be it. This is the hydrogen titration of the iron surface after various times on the stream. We have at 285 degrees C, I think it is, the transient hydrogen goes to CO hydrogen, so we accumulate this CH and the inactive C and bulk carbide for a certain period of time on the stream. We switch to helium to flush the contents of the reactor out, make the interpretation of the experiment less complicated. Then we switch to a hydrogen, and this is that's an all methane rate. There's a titration of the surface species, and this is how we know what's there. Sort of remarkable. Initially, there's the hydrogenation of the very active CH intermediate, and then only after that CH is pretty much removed from the surface, then you start to hydrogenate this surface C, and this is strange, you know, for the usual kinetics in one kind of site. You would expect the second intermediate, if it's less active, the inactive C, to just form a tail on the end of the CH hydrogenation, but that doesn't actually occur here as a second maximum, and it's difficult to explain that in terms of a single site. And so what they did come up with is believe that there are a couple of different sorts of sites going back to the self-poisoning of CH on its own reaction rate. Same sort of phenomena here. And then the third section here is the hydrogenation of the bulk carbon. And various times in the stream were used. The first peak only shows up after as little as 10 seconds on stream. If you run the reaction for much longer than that, then you will start to build in the second inactive, let's say, filamentous carbon. Now, I've said that we believe that first peak is due to CH, and that is based on an oxygen titration that Bennett and co-workers did. This is where you start up the reaction, and run the reaction for 10 seconds, CO hydrogen, purge with the helium gas, and then switch to oxygen, and burn up the CHX intermediate, and collect the water. And they measured the amount of water and figured that the stoichiometry corresponded to CH. The second peak, the inactive C, they found much less hydrogen, got it, and they obtained a stoichiometry of CH 0.17. So it's really close to zero. And for simplicity, I've called it just inactive carbon. Going now to deuterium experiments, we can, if nothing else, verify those oxygen titration results. What we're going to do here is start out again with hydrogen and make a switch to 10% CO in hydrogen at 285 degrees C in the same conditions as before, H2CO of 9. And during that CO hydrogen reaction, for 30 seconds on stream, we build up the initial CH intermediate plus a little bit of that extra carbon, and then we make a switch to CO deuterium. Now, this experiment, I think, initially done by John Happel, and there may have been some other workers who've done this. I'm not very current on this right now, but at any rate, you see during the first few seconds, deuterium dropped from hydrogen drops from 100% down to 90% in the reaction mixture, and then very quickly, because of the rapid mixing in the small reactor, we get down to essentially a zero concentration of hydrogen. During the same time, the D2 goes right up and comes close to 90% in the gas phase, and there's a spike in HD, followed by a sort of a long tail. Now we think that the spike here in the HD is corresponding to scrambling hydrogen and deuterium on the catalyst during the mixing curve. And so you've got H2 and D2 at the same time in the reactor, and an active catalyst, you make some HD. The tail here is during a period of time much after the mixing curve has expired to its final relaxation. So we think that this extra hydrogen here is mostly due to OHs on the alumina support, and possibly some of that hydrogen could be due to the CH intermediate that's scrambled off in a back reaction. And then if you follow CD4, and this is done in a high-resolution mass spectrometer, so we don't have to worry about background due to D2O, then we see that there's a slow transient relaxation of CD4 from initially 0 up to, I suppose, a couple of percent CD4. Now, it's probably intuitively obvious that this is consistent with the existence of a CHX-type intermediate. If there was only surface carbon with no hydrogen in it, you'd expect the deuterium-methane to relax statistically with the gas phase composition. And since the reactor mixing time is very short, then you should get a rapid relaxation. This is the same experiment, plus another experiment for a longer time on stream with the same nature of the experiment as CO hydrogen to CO deuterium. Times on stream were 30 seconds in CO hydrogen and an hour and a half in CO hydrogen. And have the dimensionless responses of deuterium in the gas phase and CD4. And these are normalized and dimensionless, so all we do is make the initial value 0 and force the final value of the mass spec transient to be 1.0. So in agreement with the previous figure, let's see, curve number 1 is the atom fraction deuterium in the H2 plus HD plus D2 gas, and coming out of the reactor as a function of time, and that's after 30 seconds of reaction in CO hydrogen. The curve number 2 is the same idea, except after an hour and a half on stream. And again, it's the atom fraction deuterium in the gas phase coming, well, the effluent from the reactor. The curves 5 and 6 are the CD4 transients after 30 seconds and an hour and a half on stream. And if you compare those to the others, you can, again, it's reinforced that the transient in CD4 is much slower than the deuterium transient, and all that extra space in there, time, corresponds to a CH species that prevented CD4 from being the thing produced. In other words, if you had only surface carbon with no hydrogen in it, you'd expect to just produce CD4. And to show you just how much CD4 you'd expect from surface carbon, calculated the probability of making CD4 if the precursor on the surface is only carbon, and that calculation is just to take the ZD to the 4th power. It's the probability of all the protium atoms on the methane molecule being simultaneous with deuterium. And so these curves 3 and 4, those ZD to the 4th power calculated as a function of time. And if you take, let's see, the area between the ZD to the 4th and the CD4 curves, then this area corresponds to the amount of CH on the surface of the catalyst during the reaction. At least in principle, this is all done during steady state, but iron is such a difficult catalyst to work with. We can't really do that here. Make several approximations in making these calculations. But at any rate, if you calculate how much CH is on the catalyst, after an hour and a half on stream, we calculate that there's 11 micromoles per gram of CH, whereas after 30 seconds on stream, we get about 28 micromoles of CH per gram. Incidentally, nothing in this experiment helps us distinguish between CH and CH2 and other types of intermediates. We just know that there's something with hydrogen there, there on the surface. It's interesting that we got a smaller value of CH after a long time on stream. You can do the same sorts of experiments with carbon-13, and a great number of workers have been doing experiments like this in the recent past. Beloon, Sachtler's names, Konich, Happel, Maru, several others have done experiments like this. At any rate, we get the same sort of result here. Curve A after an hour and a half on stream, and curve B after 30 seconds on stream are the transients that result. This experiment is a switch from CO hydrogen, 12 CO hydrogen to 13 CO hydrogen of the same composition. At any rate, you can go and calculate how much active intermediate you think is there based on certain rate equations and so on. Basically, they're just mass balances. And for the 13CO experiment, after an hour and a half on stream, we get 9 micromoles per gram. For deuterium experiment, we get 11. That's rather good agreement, really. For the 30 seconds on stream, we get 28 by the deuterium experiment, 35 by the 13CO experiment. So it would appear that the 13CO and deuterium experiments seem to be fairly consistent, good agreement on iron. What else can we learn about the CHX intermediate? This is probably not a good experiment to spend a lot of time on here at this point, but at any rate, we did some other more complicated carbon-13 experiments where we do things like run 12 CO hydrogen and a short period of time 13 CO hydrogen, purge with helium and then to hydrogen. What we have here is the same old titration with hydrogen of reactive surface intermediates. We have, after this extent of time on stream, we have active CH, inactive surface carbon, and in a nutshell, what this all means is we think that the active CH is very uniform in reactivity after a short period of time on stream. That might even mean that you could do ordinary kinetics on it. It's a homogeneous pool, as we say in the carbon-13 tracing literature. Then for the hour and a half on stream, much longer period of time on stream, again, the 13 carbon labeling scheme here, we make this CO hydrogen reaction, then switch to 13 CO hydrogen, then to helium, and then to hydrogen. And this helps us to label the active CH and label the bulk carbide and carbon-13. But it turns out that it takes a much longer period of time to put a 13C label on the CH intermediate. The highest concentration of carbon-13 was observed after 30 minutes exchange time. This tells us that this active CH is no longer very active after a long period of time on the stream. And it's the decay in the reaction rate corresponds to this species no longer being homogeneous. It's interesting that it seems that the species doesn't disappear. The reaction rate falls. How are you going to write a model? The reaction rate doesn't fall because the coverage of that intermediate is falling. The coverage remains the same. It's just that the turnover frequency for a portion of the intermediate becomes much smaller, so that all this reaction rate is coming from a small fraction of the active CH that's on the catalyst. The inactive filamentous carbon, let's say, doesn't convert over with carbon-13 at all, and the bulk carbide doesn't seem to scramble with the carbon-13 on the surface very quickly at all either, and that's consistent with Emmett's work much earlier. It will exchange, but we think that the rate of that transfer to the bulk carbide is less than about 5% of the synthesis rate overall. So, in summary then, for the iron alumina, we think that there's an active site S1, and initially CO dissociates to form this carbon on site 1, but this is not a very high population intermediate. The major intermediates, well, the major intermediate in the reaction is the CH on this site S1, but you can also get unreacted carbon and bulk carbides that the hydrogenation proceeds from the CH. And because of that deuterium experiment, we know now that those reactions to hydrogenate the CH are irreversible. So we just go straight away to methane seemingly without any scrambling. Now those are results made easier by high-resolution mass spectrometry. Earlier work on iron titania was more difficult. This is done on a mass spectrometer that's older than I am. At any rate, this mass spectrometer had unit resolution, so that there were several experiments with deuterium. One had to consider whether the mass 20 peak was due to CD4 plus or D2O, and it took a lot of rationalizing on the part of the authors to determine just what they were looking at. Of course, with high resolution, you don't have the problem. At any rate, this is fairly busy, but I think the take-home message here is that X doesn't equal 0 in the CHX on iron titania. In fact, Tao goes on to establish that thinks that it's simply CH on iron titania, just like the iron alumina. The transient experiment of most interest was the CO hydrogen to helium to deuterium. This is a difficult experiment to interpret, naturally, because there'll be hydrogen on the support as well, and that could give you a mixed hydrogen deuterium gas that you're going to hydrogenate the surface carbon with. But at any rate, when they ran that experiment, they didn't get much of a peak. They should have gotten, if you ran it just with hydrogen, you should have gotten a nice big peak of methane. So the methane is there, but it's not all CD4. And there is a small amount of something produced, and they think that's just D2O. So this really means then is that as long as, that X does not equal 0, that you couldn't, you had just surface carbon, then you'd expect to get plenty of CD4. So this really says that there's almost none of that. And it all has to be CHX with X not equal to 0. He goes on and does some other experiments here, like CO helium, to show that if there was C there, you could detect it by this sort of experiment, and that the hydroxyl groups on the support are important. That's probably should have said that's a low temperature reduced iron titania. And there were some other experiments done on the other mass numbers, also more difficult to interpret probably this late in the afternoon. Just moving on, the crowning experiment of this particular paper, I think, was the oxygen titration as it was performed originally on the iron alumina. And he finds here again that X is equal to 1, so it's just CH. Curve A, just a little bit about how this experiment's done. Curve A results when you run the reaction for a short period of time, and then, in CO helium to accumulate surface carbon, and so on, on a reduced catalyst, and you essentially switch to oxygen, burn that off. What they're worried about here is that you need to do the blank experiment, because when you oxidize reduced iron, there'll be a big heat effect, and this heat effect will raise the temperature of the catalyst and desorb water that's on the surface of the catalyst. So the shaded green area is the extra hydrogen or water due to the CHX, and stoichiometry works out to be CH again. So for the last catalyst, nickel on alumina, we have some of these sorts of physical properties. Same supports, the V tier is about the same. I think that there's about 300 surface nickel sites, and that corresponds to a diameter by X-ray of about 50 angstroms for the nickel crystallite size. And there should be about 95% reduction of the nickel on alumina to nickel 0 during the reduction at 450 degrees C overnight. Back to the titration of the steady state surface with hydrogen. You run the reaction in CO hydrogen and then switch to hydrogen itself. You'll reduce the nickel you have surface CO, and you also have surface CHX. So you'll get a peak of a certain shape, and that's the, well, here in an ordinary experiment, it's the same as this 12 CH4 plus 13 CH4. If you didn't use isotopes, you just get this nice initial peak here, and then a tailing off. This experiment's done in 5H2Cl. It's 10% hydrogen, 50%, 10% CO, 50% hydrogen balance helium at 1 atmosphere or 250 degrees C. We've done an isotopic deconvolution here, and this is 5 minutes on stream. So what that experiment is a 12 CO hydrogen, then switching to 13 CO and helium. If you have no hydrogen, the reaction shuts down. So you have a 13 CO helium, the reaction shuts down, and the surface CO converts over to 13 CO. And then we switch again to hydrogen, and what happens is we're able to deconvolute the original methane peak into two contributions. One is 12 CH4 that didn't exchange, and the other is 13 CH4 that did, so that the exchangeable portion of this methane peak, so to speak, came from the CO, and the non-exchangeable portion was from the CHX on nickel. So there's two different intermediates on the nickel, just like with ruthenium and rhodium. There's about a half a monolayer of CO, and there's probably about a half a monolayer of CHX under these conditions. So we move forward and try to determine what that CHX species is. We did a couple of different things. Richard Underwood ran the oxygen experiment taken from the ironwork, and we weren't able to detect any H in the CHX there, so the oxygen experiment on nickel seems to indicate that we have just surface carbon with no hydrogen on it. Another experiment was a non-intensive but nevertheless infrared examination of the surface under steady-state reaction conditions, and we weren't able to observe any carbon-hydrogen stretching frequencies in the IR. And the last thing that we did was a deuterium experiment, and this is the result of that. It's unfortunately an issue here by having this plotted in this sort of a dimension, which you'll see the reason for that in a minute. We made the switch from CO hydrogen after 5 minutes on stream to CO deuterium. It corresponds to the same conditions as the previous slide, so we know there's plenty of CHX there. And when we do that and monitor the CD4, we see that the CD4 relaxes every bit as fast as the deuterium gas phase does. And this is completely unlike the iron experiment, the iron catalyst results, where we found that the CD4 relaxed something like this. CD4 on iron. So it would appear that each of the experiments on nickel are self-consistent with one another, that we're finding no CHX on nickel. And just to, well, let's do one thing at a time, to show you what the carbon-13 results look like on the same time scale, up to 7 minutes and Z between 0 and 1. The carbon-13 experiment relaxes very slowly, so you have plenty of CHX according to the carbon-13 experiment. And just overlaying, we found no CHX by the COD2 experiment. So our conclusion is that there's no CHX on nickel, and we believe that there's just an active surface carbon on the nickel during that reaction under those conditions. It's not an airtight argument, naturally. It's always difficult to prove something positively, but all the evidence is pointing that way. Any questions?
Well, if we have no questions, I certainly thank the speakers for participating in this session on isotopes. Again, thanks.